Hello, everybody. Welcome to my talk. My name is Michal, and I'm going to talk about parameterized gap amplification. I hope you'll enjoy it. The plan of the talk is as follows. I'll begin with the idea of gap amplification technique and the framework for proving hardness of approximation. Then I'll introduce the Steiner Orientation problem and construction for proving hardness for this particular problem, which is quite elegant in my opinion, and implications of that. So let us start. The basic idea I will talk about is a gap problem, and it appears when we have optimization problem. I will talk only about maximization problems, and its gap versions is a task of distinguishing instances with large solutions from those with small solutions. So here we have formally two languages, L1 and L2, of instances with big opt and low opt. And one can see that if we had a approximation algorithm with approximation factor better than Q, which is the gap in here, then we could distinguish these two cases. So proving hardness of a gap problem implies hardness of approximation. And we can consider gap preserving reductions. In the basic setting, we are interested in polynomial time approximation algorithms and polynomial hardness. And such a reduction should work in polynomial time, produce a polynomial size instance, and preserve these two languages, L1 and L2. And if you could distinguish these two cases on the right, then it would imply that we can distinguish them on the left. So in order to prove hardness of approximation, we can employ such reductions, but we should begin with some problem for which we know that its gap version is hard. So to obtain that, we can start with a conjecture stronger than P unequals NP, say unigame's conjecture, which already states hardness of a particular gap problem. But we don't want to use any such strong conjectures. So what is the other way to obtain hardness of gap problems? Consider unweighted maximization problem with an instance of size n, and for simplicity, I just represent those big and small instances as like fraction of how large the optimal solution is. So the language L1 consists of instances with the solution of size n, and L2 consists of instances with solution n times 1 minus epsilon at most. And suppose that we have a gap preserving reduction which increases the gap slightly and increases the size of the instance by a constant factor. It's a self-reduction from the same problem to itself, but only with a larger gap. So we can compose this reduction many times, and we still get a gap preserving reduction. And idea is that we can treat epsilon as something not necessarily constant. We can set epsilon to be 1 over n, and we can make a chain of those reductions of length log n, and then this combined reduction is still polynomial. And since the epsilon is 1 over n, then in fact on the left we obtain original problem with no gap. So this is just distinguishing between having a solution of size n or not. And such a construction is possible for the max CSP problem, which is NP hard. And this is actually equivalent to the famous PCP theorem, which provides NP hardness for many gap problems. So let us see how this can work in parameterized complexity. So instead of polynomial reductions, now we consider parameterized reductions, and so parameterized gap preserving reductions, and we consider problems parameterized by the size of solution. And again, if we have such a reduction and we could distinguish those two cases on the right, then it follows that we also can solve this problem on the left. And again, in order to prove a hardness of a specific gap problem, we need to begin with some hard gap problem. And to do so, we can again use some strong conjecture as gap exponential time hypothesis, which states that one cannot approximate max reset in sub-exponential time, and this provides hardness of gap version of k-clique. But we don't want to do this. We would like to employ this idea from PCP theorem and try to combine a chain of reductions, FPT reductions this time, and now we allow that size of the new instance can be n times some function of the parameter. And now if we compose this reduction t times, then if t is constant or t is function of the parameter, we still obtain FPT gap preserving reduction. And if we again set initial gap to be subconstant, to be k over k minus 1, where k is parameter and the solution size, then we again can begin this chain of reduction from a problem with no gap. And if we can grow this gap to arbitrarily large constant, we can make a connection between the original problem and its gap version. So if the original problem is W1 hard, then we obtain that its approximation version is also W1 hard. So it's unlikely to admit an FPT approximation algorithm. This idea can be also employed to prove super constant hardness of approximation, but in order to do so, we need to keep track of how fast the parameter k and the gap q is growing in this chain of reductions. So the rule of thumb is the slower the parameter grows and the faster the gap grows, the better lower bounds we can obtain. Let's move on to the Steiner orientation problem. So in this problem, we are given a mixed graph, so a graph with both directed and undirected edges. We can see an undirected graph on the left and a mixed graph on the right, with these two edges having fixed orientations. And we are given k terminal pairs with source S and sink T. And we ask whether we ask for an orientation of the undirected edges that would maximize the number of paths from source to sink. And the parameter is the number of terminal pairs. And in this example on the left, we can find orientation like this, which would provide paths for every source sink pair. And one can see that each edge can be used for many terminal pairs at once. And in the example on the right, with those two edges already oriented, we can satisfy at most 2 requests, but not all of them. So what is known about this problem? It it becomes relatively simple when the graph is undirected, and the maximization version is FPT. Then for general mixed graphs, the best known running time is roughly n to the k, which means that the problem belongs to the class XP, and it was open for a few years whether it admits whether it is FPT, and it turns out it's unlikely because it is W1 hard. When it comes to approximation, assuming gap ETH, one can rule out some small constant approximation, and also this result shows that this n to the k running time is essentially tight. A similar result also holds for a polynomial time approximation, and note that these two results are incomparable because this gap ETH is a stronger assumption. And it is not known whether it admits some constant approximation for some large constant in any of these regimes, and I'm going to address this question right now. And I'm going to represent an instance with such a blue box with sources being the circles at the bottom and the sinks being the circles at the top. And whenever an orientation gives a path between a terminal pair, then I will draw them in gray, otherwise in white. So let us consider some instance and make k+1 copies of it. Put k copies at the bottom and 1 copy in the new layer at the top. Now we connect these instances as follows with tuple k tuple R representing which sink from the first copy is getting connected to the first source here, and so on. And we're gonna consider a gadget with k terminal pairs with sources and sinks indicated with orange. So now consider such a gadget and see what would happen if we fixed an orientation in the bottom layer. So if the instance is not fully satisfiable, then in each blue box we will have at least one white circle, so a source which is inactive, it is not connected from the sink, that is not connected from the source, and we will use a tuple C called configuration to specify where these white circles are. So now let us consider such a thought experiment that we fix this configuration and consider a random process of sampling R and choosing those connections. So whenever we've chosen an edge outgoing from a white inactive sink, then we know that we cannot extend it. And let us consider two random variables, y and x. And y is the fraction of edges that are connected to gray sources, so gray sinks, so they can be extended. And x specifies what's the maximal fraction of these paths that can be extended at once through this top layer. So x is upper bounded by y, and on this example we can see that y is 3/4 because here we have one arrow going out from white circle. And by linearity of expectations, we can see that the expected value of y is at most 1 minus 1 over k, because this is just the probability of choosing a gray circle. And this upper bounds the expected value of x. So far, nothing fancy is happening. But let us consider a slightly different tuple R, in which we have all arrows going out of gray circles. So right now, the value of y is 1. So each path can be extended when looking only at its own. But if we consider an instance that is not fully satisfiable, then we cannot extend all those paths through this upper blue box. So so here the value of x is less than y, and from that we can conclude that the difference between these random variables is positive with a positive probability. So the expected value of x is slightly less than expected value of y, which is 1 minus 1 over k. So let us use this insight to construct a reduction. So let us consider all possible tuples R. There are k to the k of them, and for each such R, we construct the gadget from the previous slide. We add k terminal pairs and take a union of them. And the nice thing is that right now, for any fixed configuration at the bottom layer, the behavior of such an instance is exactly the same as before. That the maximal fraction of satisfied terminals is exactly the average over all the gadgets. So this provides us a slightly larger gap, like a foot in the door, a gap that we are going to amplify. And of course, if we started with a yes instance, with an instance where all sourcing pairs are satisfiable, then we can use this orientation in each blue box, and this new big instance also would be fully satisfiable. So we get completeness and soundness of the reduction. So we introduced some small gap, and let us iterate this process right now. So we can take, say, the large instance that we just constructed and use it as an input to the next step. So make k copies of instance hi, and again consider all possible tuples R, and take copies of the initial instance. And by the same argument as before, we can conclude that the gap in the following instance would be slightly larger than before, and this additive change between q, between the value of the gap, can be proven to be independent of I. So at each step we add some epsilon k. So when we go back to our scheme of the chain of reduction, we can see that we obtain exactly that we wanted. We began with a trivial gap, k over k minus 1. So the initial instance on the left we started from is a no gap instance, and we can grow this gap to arbitrary large constant. So this way we can rule out FPT constant approximation for Steiner orientation. So I mentioned that this can be also used to rule out super constant approximation, and to do so we need to keep track how fast the parameter is growing. So far we haven't been too much economical, like this number of terminal pairs is growing quite rapidly. And let us go back to the first step, and let's try to do this in a slightly smarter way. So consider setting a first gadget with the tuple R governing these connections randomly, and repeat this process m many times. This is very similar to what happened before, but instead of taking all k to k choices of R, now we only take m of them. And I'm gonna try to convince you that we don't need this m to be super large. And to do so, I will take advantage of the Chernoff bound. So for each configuration, for each orientation in the bottom layer, the maximal fraction of terminals that we can satisfy is again the average over all gadgets. And since we sampled these tuples R randomly and independently from each other, then we can use Chernoff bound to upper bound how far this average can be from the expected value of x. So this was this average when we considered all possible tuples, and since these are quantities between 1 and 0, then Chernoff bound enjoys such a nice form. So we can see that setting m roughly proportional to k log k gives a bound of going far from the expected value, which is of magnitude k to minus k. And here is the thing. We can ask how many possible configurations to consider there are, and this is the number of choices of where are the white circles, and there are k to k of them. So now when we can bound this probability to be such small, then by simple union bound, we can deduce that for any configuration, for any behavior at the bottom layer, we actually have roughly the same behavior as in the previous construction with k to k tuples. And in the construction, we're gonna set this delta, this deviation, to be smaller than epsilon k, our additive change in the gap. The presented construction gives a following lemma that for any parameter q, we have a FPT gap preserving reduction from a no gap problem to the gap problem with gap being q, and the new parameter being double exponential in k log q. So direct corollary of that is that a constant FPT approximation is W1 hard, but we can also rule out sub-logarithmic approximation, and this is because of this double exponential dependency over there. And if we had a single exponential dependency, then we could make a sub-polynomial lower bound in here. This also implies that polynomial time constant factor approximation is not possible assuming FPT unequals W1. But for purely polynomial time, we can also use this lemma in a slightly different way. Namely, we can treat K and Q as slowly growing functions of n, and then we can prove a lower bound with approximation factor being a function of n, which is more typical in a theory of polynomial time approximation. And the little caveat in here is that this argument with Chernoff bound is randomized, and in an FPT reduction we can afford to randomize it, but in the polynomial time reduction we don't have enough running time, so the reduction is randomized, and we need to assume that W1 doesn't admit randomized FPT algorithm, and this is why I put a star in this theorem. So that's all. There are some more theorems in the paper, but I don't have time right now to cover them. So if you like the talk, be sure to check out the paper, and see you at the Q&A.